Imagine standing alone on a silent hilltop at midnight, gazing upward at the endless canopy of stars. The sky seems eternal, as though it has existed forever, stretching beyond the limits of imagination. Yet, the deeper we look, the more pressing the question becomes. Where did it all come from? The shimmering constellations, the glowing band of the Milky Way, and the faint whisper of galaxies. Billions of light years away, all of them carry a hidden story. That story, according to modern science, begins with what we call the Big Bang. For thousands of years, humans tried to explain the origin of the heavens through myths, legends, and philosophy. Ancient Egyptians believed the sky was the goddess Nut arching her body over the earth. In Norse mythology, the sky was crafted from the skull of a giant. Meanwhile, Greek philosophers like Aristotle argued that the universe had no beginning, that it simply existed in a timeless, eternal state. These ideas comforted civilizations for centuries, giving them an image of a sky that was permanent and unchanging. But the rise of modern science began to tear away those comforting illusions. With the invention of telescopes, astronomers discovered that the heavens were far more vast and dynamic than imagined. Stars were not fixed lights embedded in a celestial sphere, but colossal suns scattered across unimaginable distances. Galaxies, swirling islands of billions of stars, stretched into the darkness. Suddenly, the question of origins became more urgent. If the cosmos was not eternal, then how and when did it all begin? The Big Bang Theory emerged as a radical answer to this age-old mystery. It proposes that the universe began around 13.8 billion years ago from a state of infinite density and heat singularity. From this inconceivable beginning, space itself began to expand. It wasn't an explosion in pre-existing space. Rather, it was the birth of space and time themselves. Everything matter, energy, galaxies, stars, planets, and eventually escaped into existence through this cosmic unfolding. To grasp the scale of this event, picture the entire universe compressed into a point smaller than an atom. Temperature soared beyond anything we can imagine, and the laws of physics as we know them today simply did not apply. Within a fraction of a second, this singularity began to stretch outward, faster than the speed of light, in an event known as cosmic inflation. That rapid expansion set the stage for the structure of the cosmos, the vast web of galaxies and clusters that we observe through telescopes today. At first, the idea of the Big Bang sounded outrageous. To many, how could everything space, time, and matter come from nothing? Critics dismissed it as absurd or unscientific. In the mid-20th century, rival theories like the steady-state theory argued that the universe had no beginning, that it was eternal and constantly replenishing matter as it expanded. The scientific community was divided, and for decades, fierce debates raged over whether the universe had a birth or had always existed. Yet, evidence slowly began to mount in favor of the Big Bang. The first hints came from the work of Edwin Hubble in the 1920s. Using the Mount Wilson Observatory in California, Hubble studied distant galaxies and discovered something astonishing. Almost all of them were moving away from us. Not only that, but the farther away a galaxy was, the faster it seemed to recede. This observation became known as Hubble's law, and it implied that the universe itself was expanding. If the universe is expanding now, then by running the clock backward, everything must have once been closer together. Following this logic, scientists concluded that all matter and energy must trace back to a single origin point. Cosmic beginning. Hubble's discovery was like a crack in the wall of eternity, revealing that the universe might not be infinite and timeless after all, but rather dynamic and finite in age. Still, the Big Bang needed more than Hubble's observations to become a widely accepted theory. In the 1940s, scientists George Gamow, Ralph Alph, and Robert Herman predicted that if the universe began in a hot, dense state, then it should have left behind a faint afterglow of radiation. This relic heat, stretched across the cosmos, would serve as the smoking gun of creation. Yet, for years, no one could find it. Then, in 1965, two engineers working at Bell Labs, Arno Penzias and Robert Wilson, stumbled upon a mysterious hiss of microwave radiation coming from every direction in the sky. At first, They thought it was interference caused by pigeon droppings in their antenna. But after careful testing, they realized this faint radiation was real and cosmic in origin. They had accidentally discovered the cosmic microwave background, CMB, the very afterglow of the Big Bang predicted decades earlier. The CMB was a game changer. It provided overwhelming evidence that the universe did indeed begin from a hot, dense state and had been cooling and expanding ever since. Suddenly, the Big Bang was no longer a fringe idea but the leading theory of cosmology. The afterglow of creation itself had been found, frozen in time, whispering across the heavens as proof of the universe's fiery birth. Beyond its scientific significance, the Big Bang reshaped how humanity saw itself. If the universe had a beginning, then everything within it, galaxies, stars, planets, and life, was part of an evolving story. The sky was not a static dome of eternal light, but a living, dynamic cosmos that had grown and transformed over billions of years. Humanity, in turn, was no longer separate from this story, but deeply woven into it. For many, this idea was both humbling and exhilarating. It suggested that the atoms in our bodies were forged in stars that themselves were born from the chaos of the early universe. We are, in a very literal sense, children of the Big Bang, made of stardust, bound by the same cosmic history as the galaxies above. Yet, despite its triumphs, the Big Bang theory leaves many unanswered questions. What caused the singularity to exist in the first place? Why did it expand? Was there something before it? These mysteries push the boundaries of both science and philosophy, reminding us that the universe still holds secrets beyond our reach. As we explore these questions in the coming chapters, we will trace the journey of scientific discovery, the evidence that supports the Big Bang, and the strange implications it has for our understanding of reality. From the earliest moments of cosmic inflation to the formation of galaxies and stars, each step brings us closer to understanding the sky above. The Big Bang is not merely a scientific theory, it is a lens through which we see our place in the cosmos. It tells us that the night sky, with all its beauty and immensity, is the product of a grand unfolding that began with a single spark. That spark lit the path to everything: time, space, and existence itself. As you look up at the stars tonight, remember, you are witnessing light that has traveled for billions of years, crossing the expanding fabric of space to reach your eyes. Every twinkle carries a message from the past, a reminder that the universe is both ancient and alive. In its silence, the sky tells the story of its own beginning. This is where our journey begins, with a universe that started small, burned bright, and grew bust. A universe that continues to expand, carrying us along in its endless voyage. The Big Bang may have been the beginning, but it is also a never-ending process, shaping the heavens above and the life below. The story of the Big Bang is the story of us all. It is the history of the sky, the earth, and the beating heart within your chest. It is a cosmic narrative that links the human soul to the birth of the stars, and it all began with a moment-on instant that created everything. To understand that first moment, scientists study not only the galaxies, but the subatomic particles that once ruled the infant cosmos. Within the first microseconds, the universe was a seething ocean of quarks and gluons, the raw ingredients of matter. As it cooled, these particles began to combine, forming the protons and neutrons that would one day build atoms, stars, and worlds. Imagine a universe no larger than a grapefruit, but hotter than the core of a million suns. In this fiery cradle, the fundamental forces of gravity, electromagnetism, and the nuclear forces began to take shape. What we now see as stable and orderly laws of physics were once born in chaos, carved into existence by the first breaths of the cosmos. As the universe expanded and cooled further, the first atoms began to form. Hydrogen and helium dominated, the simplest and lightest elements, yet they were enough to ignite the engines of creation. These elements would one day collapse into the hearts of stars, fusing into heavier elements, and eventually giving rise to the chemistry of life. In this sense, the Big Bang was not just a beginning but a seed. It contained within it the blueprint for everything that would follow: solar systems, oceans, forests, and even human thought. The night sky is a reminder that we live inside that seed's unfolding story. Each star, a chapter. Each planet, a word. and each life a sentence in the grand cosmic book. Some may ask, if the universe came from such a tiny singularity, what came before it? This question remains one of the greatest mysteries of science. Some theories suggest there was no before, that time itself was born with the Big Bang. Others speculate about cycles of expansion and collapse, an eternal rhythm of creation and destruction. The question of origins pushes us to the very limits of human understanding. Physicists attempt to probe it with equations and particle accelerators, while philosophers wrestle with its implications for existence itself. Does the Big Bang point to a deeper cause, or is it the ultimate reality, needing no explanation beyond itself? Whatever the answer, one truth is certain. The Big Bang connects us all. Every galaxy and every star shares the same origin. The vast distances that separate us are bridged by a common beginning. The sky above, in all its enormity, is not random. It is part of a single unfolding process that began 13.8 billion years ago. As the evidence piled up, the Big Bang theory became more than a hypothesis, became the foundation of modern cosmology. Satellites like COBE, WMAP, and Planck have mapped the cosmic microwave background with stunning precision, revealing tiny fluctuations that seeded the growth of galaxies. These discoveries confirm, with overwhelming detail, the narrative of a universe born in fire and sculpted by time. And yet, mystery remains. Dark matter and dark energy and forces that shape the cosmos are still poorly understood. They hint that the Big Bang, while powerful, is only part of the story. The sky above us is not merely a relic of the past, but a living laboratory, urging us to ask new questions, to seek new answers, to continue the search for meaning in the stars. So when you gaze at the heavens, remember that you are not just an observer, you are a participant. Your atoms were forged in the nuclear furnaces of ancient stars, and those stars were born from the chaos of the Big Bang. You are the universe, contemplating itself, a fragment of eternity reflecting on its own beginning. The Big Bang is not the end of the story, it is the prologue. As our journey continues, we will dive deeper into the evidence, explore the challenges, and confront the profound implications of living in a universe with a beginning. This is only chapter 1, but already the sky has revealed its greatest secret, that everything we see and everything we are began with a single, magnificent burst of creation. In the quiet dawn of the 20th century, most scientists believed the universe was static and eternal. The sky above seemed unchanging, the stars fixed in their positions like diamonds set in stone. The very idea that the cosmos could grow or change was unthinkable to many scholars of the time. Yet, hidden in the faint light of distant galaxies lay secrets that would soon transform this ancient belief. The first revolution came from the discovery of galaxies themselves. For centuries, astronomers debated whether spiral nebulae, faint cloud-like smudges seen in telescopes, were part of the Milky Way or distant worlds of their own. The debate raged until the 1920s, when Edwin Hubble and his colleagues measured the distance to the Andromeda Nebula, revealing it was far beyond our galaxy. Overnight, the universe became far larger than anyone had dared imagine, but Hubble's greatest contribution was still to come. At Mount Wilson Observatory in California, he used the powerful 100-inch Hooker telescope to study galaxies across the sky. By analyzing the light they emitted, he noticed something extraordinary. The light from most galaxies was redshifted, stretched to longer wavelengths, as if the galaxies were racing away from us. This phenomenon, known as the redshift, became one of the most important clues in cosmology. The farther a galaxy was, the greater its redshift appeared. It was as though space itself was expanding, dragging galaxies apart like raisins in a rising loaf of bread. This discovery became known as Hubble's law, and it shook the foundations of astronomy. If galaxies were moving away, logic suggested that in the distant past they must have been closer together. Run the cosmic clock backward, and all matter and energy must converge into a single origin. Though Hubble himself was cautious in his conclusions, the implication was unavoidable. The universe had a beginning. The notion of a universe with a starting point was both thrilling and troubling. For many scientists, it sounded uncomfortably close to the idea of creation, a concept they preferred to avoid in scientific discourse. Others clung to the steady-state theory, which argued that while the universe expanded, New matter continuously formed to keep its density constant. In T's model, the cosmos had no beginning and no end. The battle between Big Bang and steady-state theories became one of the most intense debates in 20th century science. Supporters of the steady state liked its elegance and its alignment with the old idea of an eternal universe. But Big Bang proponents pointed to the growing mountain of observational evidence in their favor. By the mid-20th century, the Big Bang was gaining momentum. Theoretical physicists began to explore what such a beginning would look like. They calculated that a hot, dense early universe would not only produce galaxies but also leave behind chemical fingerprints in the form of light, elements hydrogen, helium, and trace amounts of lithium. If these predictions matched the composition of the cosmos, it would be strong evidence for the theory. Observations soon confirmed that about 75% of the universe was hydrogen and about 25% helium, with only tiny amounts of heavier elements. This fit perfectly with Big Bang predictions. The stars had not created these elements. They were relics from the first minutes of the universe itself, forged in the searing fireball of creation. Still, many scientists demanded stronger proof. If the universe began in a hot, dense state, then its radiation should still linger, stretched and cooled by billions of years of expansion. In the 1940s, physicists George Gamow, Ralph and Robert Herman predicted that this leftover glow called the cosmic microwave background would fill all of space at just a few degrees above absolute zero. But for years, no one had the technology to detect it. Then came a twist of fate. In 1965, Arno Penzias and Robert Wilson, two engineers at Bell Labs in New Jersey, were building a radio antenna for satellite communication. They kept encountering a persistent hiss of microwave noise no matter where they pointed the antenna. They cleaned the equipment, removed pigeons roosting in the dish, and tested everything. But the hiss remained. Unbeknownst to them, a group of physicists at Princeton University, just 30 miles away, had been preparing to search for the very signal Gamow and his colleagues predicted. When they learned of Penzias and Wilson's strange noise, they realized it was no accident. The engineers had stumbled onto the relic radiation of the Big Bang, the faint afterglow of creation itself. The discovery of the cosmic microwave background, CMB, was like striking gold. Here was direct, physical evidence that the universe had indeed been born in a hot, dense state. The steady-state model could not explain it, but the Big Bang theory predicted it perfectly. Almost overnight, the scientific debate shifted. The Big Bang had emerged as the dominant explanation of cosmic origins. Over the following decades, technology advanced to study the CMB in extraordinary detail. Satellites like COBE, WMAP, and later Planck measured its faint ripples, showing tiny fluctuations in temperature across the sky. These patterns revealed the seeds of galaxies' minute variations in density that gravity would amplify into stars, clusters, and the vast cosmic web. The precision of these measurements stunned the scientific world. The Big Bang was no longer a vague theory, it was a detailed model supported by overwhelming data. The radiation left behind by the universe's birth was mapped like a photograph of its infancy, showing us the cosmos as it appeared just 380,000 years after its beginning. But Hubble's discovery and the CMB were not the only clues. Astronomers also found that the universe was not just expanding. Distant supernova appeared dimmer than expected, suggesting that some mysterious force was pushing galaxies apart faster and faster. This force became known as dark energy, and though it remains one of the greatest mysteries of modern physics, it reinforced the idea that the universe had a dramatic and dynamic beginning. The combination of redshift, light element abundances, and the CMB formed a triumphant trinity of evidence. Together, they painted a consistent picture of a universe with a fiery birth and a long history of expansion. What was once controversial had now become the cornerstone of cosmology. Yet even with its success, the Big Bang theory did not answer everything. It described how the universe expanded, but not why. It traced matter and energy back to a singularity, but could not explain what caused that singularity or what, if anything, came before. These questions remain tantalizing mysteries at the edge of science. For philosophers, the Big Bang raised profound questions about existence and meaning. If the universe had a beginning, does it suggest a deeper purpose? Or is it simply a natural event, the result of physical laws we do not yet fully understand? For many, the theory was not just a scientific breakthrough but a philosophical challenge. Scientists, however, pressed on with observations. The night sky became a laboratory, each photon of starlight carrying clues from the past. Every telescope pointed at the heavens was, in essence, a time machine, peering deeper into the story of creation. The further we looked, the closer we came to the first moments of the Big Bang. Hubble's legacy grew as astronomers used more advanced instruments. From the Hubble Space Telescope to the James Webb Space Telescope, these observatories revealed galaxies forming just a few 100 million years after the Big Bang, showing us snapshots of the universe's childhood. The data consistently aligned with Big Bang predictions, cementing its place as the foundation of modern cosmology. Still, the steady-state theory did not vanish overnight. Its supporters continued to argue for decades, searching for loopholes and alternative explanations. But the weight of evidence became impossible to ignore. As the data piled higher, the Big Bang transformed from a radical idea into an accepted scientific reality. One of the most powerful aspects of the Big Bang theory is its ability to make predictions. It does not simply describe the universe as we see it. It forecasts what we should find if the theory is correct. Time and again, observations have confirmed these predictions, strengthening its credibility with each new discovery. Even so, cosmologists remain cautious. They know that scientific theories are always provisional, open to refinement or replacement if new evidence demands it. The Big Bang, while overwhelmingly supported, is not the final word. It is the best model we have today, a guiding framework that points the way to deeper truths. For the public, the Big Bang captured the imagination like few other scientific ideas. It offered a grand, unifying story of the cosmos, from the smallest particles to the largest galaxies. It linked humanity to the stars, showing that our existence was part of a cosmic narrative billions of years in the making. Popular culture embraced it too, with documentaries, books, and even comedy shows borrowing its name. The phrase Big Bang entered everyday language, becoming shorthand for beginnings, explosions, and dramatic change. What began as an abstract scientific theory had become part of human culture. Yet, the scientific heart of the theory remains the fact that we can trace the origin of the universe, using mathematics, telescopes, and radiation left over from its birth, is a triumph of human curiosity. It shows the power of observation, imagination, and persistence in uncovering the deepest truths of existence. The night sky, once thought eternal and unchanging, is now understood as a dynamic record of cosmic history. Every star and galaxy is evidence of a universe that began in fire and continues to evolve. The heavens are not silent, they are alive with the echoes of the Big Bang. For those who seek meaning, the Big Bang is both humbling and empowering. It tells us that we are small, yet significant, fleeting, yet connected to something eternal. It reminds us that the atoms in our bodies are ancient travelers, born in the first seconds of creation and carried across billions of years to form us. Chapter 2 closes with this thought. The Big Bang is more than a scientific theory. It is a story of discovery, a testament to the human spirit's desire to know where we came from. The evidence is written in the stars, in the radiation between galaxies, and in the elements of our very body. And though many mysteries remain, one truth is clear. The universe has a history, and it began with a burst of unimaginable brilliance. To truly understand the birth of the universe, we must journey back to its earliest moments, fractions of a second after the Big Bang. In this incomprehensibly brief period, the cosmos underwent a transformation so rapid and dramatic that it defies intuition. This event is known as cosmic inflation, a sudden expansion that stretched the universe faster than the speed of light itself. Inflation did not occur within space, it was space itself expanding. Imagine a balloon swelling instantly from the size of an atom to something larger than a galaxy. The fabric of space stretched so violently that tiny quantum fluctuations, microscopic ripples in energy, were magnified to cosmic scales. These ripples would later grow into the galaxies, stars, and planets we see today. For less than a trillionth of a second, the universe inflated exponentially, smoothing out any irregularities and creating the near-uniform cosmos we observe. Yet, inflation also planted the seeds of structure, slight variations in density that would one day become the cosmic web. Without inflation, the universe might never have developed the complexity that allowed life to exist. As inflation slowed, the universe entered a fiery state of unimaginable density and heat. Temperatures reached billions of degrees, and energy condensed into a seething soup of fundamental particles, gluons, electrons, and photons, colliding in an endless storm. Within minutes, this storm cooled enough for quarks to bind together, forming protons and neutrons. These building blocks then combined into the first atomic nuclei: hydrogen, helium, and traces of lithium. This process, known as Big Bang nucleosynthesis, provided the raw material for everything to come. The newborn universe was still opaque, filled with a dense plasma of particles and radiation. Light could not travel freely. It scattered constantly off charged particles, trapped in an endless cosmic fog. It would take hundreds of thousands of years for this fog to clear. About 380,000 years after the Big Bang, the universe cooled enough for electrons to join atomic nuclei, forming neutral atoms. This event is called recombination, and it was revolutionary. For the first time, light could travel through space without constant scattering. The moment light broke free, it filled the universe with a soft, uniform glow. This radiation is the cosmic microwave background (CMB. The faint afterglow of creation itself, still visible today as microwave radiation permeating every corner of the sky. At first glance, the CMB looks uniform, almost featureless, but with sensitive instruments. Scientists discovered tiny variations in temperature ripples, only a few parts in 100,000. These ripples carried the fingerprints of inflation, encoding the seeds of all cosmic structure. Where the CMB was slightly denser, gravity would later pull matter together, forming galaxies and clusters. Where it was slightly thinner, vast cosmic voids would emerge. The entire architecture of the universe to grant cosmic web stretching across billions of light-years was written into these ancient ripples. To map this faint glow, scientists launched satellites such as COBE in 1989, WMAP in 2001, and Planck in 2009. Each mission revealed the CMB with greater clarity, painting a baby picture of the universe as it appeared just 380,000 years after its birth. The images stunned the scientific community. They showed not only the age of the universe with incredible precision, but also its composition. Ordinary matter, and dark energy. The CMB became a cosmic Rosetta Stone, decoding the universe's past, present, and future. The fact that we can observe this ancient light is astonishing. Every photon of the CMB has traveled for over 13 billion years, crossing the expanding fabric of space, untouched by stars or galaxies, to finally arrive at our telescopes. It is the oldest light in existence, a direct message from the dawn of time. This discovery also highlighted the elegance of inflation theory. The tiny quantum fluctuations magnified during inflation matched the ripples observed in the CMB. In other words, the universe's vast structure grew out of quantum jitter, microscopic randomness, blown up to cosmic scales. It is almost poetic. The chaos of the quantum world gave birth to the order of galaxies, planets, and life. The randomness of subatomic particles became the blueprint of the Milky Way, of Earth, and of us. Without those tiny imperfections, gravity would have had nothing to work with. A perfectly smooth universe would have remained a cold, empty void. It is only because of slight irregularities in the CMB that stars were born, that galaxies spun into existence, that life could emerge to wonder at the sky. In this way, the CMB is more than a scientific discovery. It is a reminder of our improbable existence. It tells us that the universe is not perfect, and in its imperfection lies the very possibility of beauty and complexity. Scientists today continue to study the CMB with extraordinary precision, searching for even subtler clues. They hope to detect the faint signature of gravitational waves ripples in spacetime from the earliest moments of inflation. If found, these would confirm the theory of inflation beyond doubt, but the search is difficult. The signals are faint, hidden beneath the noise of galaxies and interstellar dust. Instruments must be cooled to near absolute zero and launched into space to escape Earth's atmosphere. It is a quest that requires patience, precision, and imagination. Still, the potential reward is staggering. A glimpse into into the universe's first instant, when the laws of physics themselves may have been forged. The CMB is like a veil, and behind it may lie secrets of quantum gravity, extra dimensions, and the true origin of space and time. The CMB also challenges us philosophically. It suggests that the universe is not only knowable, but that its earliest moments are imprinted into the sky itself. The heavens are not silent. They are archives, carrying messages across billions of years for us to decipher. This realization has profound implications. It means that by looking outward, we are also looking backward, peering into our own origins. The atoms in our bodies trace their lineage to those first ripples, to the plasma that once filled the young cosmos. Every time we switch on a television or radio, traces of the CMB appear as static. It is humbling to realize that the hiss of static noise is, in part, the echo of creation. The universe still whispers its birth into our daily lives. The study of the CMB has also confirmed the geometry of the universe. Its patterns reveal that space is flat on the largest scales, not curved like a sphere or saddle. This finding supports inflation and reshapes our understanding of cosmic destiny. A flat universe means that its expansion may continue indefinitely, driven by dark energy. The sky we see today is not the final chapter, but an unfolding story, one whose ending remains uncertain. Looking at the CMB is like holding a cosmic baby picture, frozen in time, yet it is also a mirror, showing us how fragile and improbable our existence truly is. Without those ancient ripples, Earth and humanity would never have come to be. The fact that we can understand this, that our species can decode the faintest whispers of the cosmos, is itself remarkable. It speaks to the power of human curiosity, of minds daring to look beyond survival and into the stars. The CMB is a scientific triumph, but it is also a human one. It bridges the gap between mathematics and meaning, between the coldness of physics and the warmth of wonder. It tells us not only how the universe began, but also why we feel compelled to ask. As we look deeper into the CMB, we are reminded of how much we still do not know. The early universe remains a mystery, a puzzle waiting for new generations of scientists, dreamers, and explorers to solve. Chapter 3 closes with this thought. The sky above us is not just a spectacle, it is a story written in light. The faint glow of the CMB is the universe's first chapter, an ancient message that says, "I began here, and from this beginning, all things followed." After the glow of the cosmic microwave background faded, the universe entered a period of profound darkness, known as the Cosmic Dark Ages. This era stretched for hundreds of millions of years. No stars burned, no galaxies glowed, only a vast sea of cold hydrogen and helium drifted silently through space. Though empty to the eye, this darkness was far from still. Tiny fluctuations in density, imprinted during inflation, slowly grew under the pull of gravity. Over millions of years, invisible scaffolds of dark matter gathered, pulling ordinary gas along with them. In this silent ballet, the first cosmic structures began to form. Clouds of hydrogen and helium collected in dark matter halos, gradually growing denser. Though invisible at first, these clouds were the cradles of creation, destined to ignite the first stars. Imagine the universe as a vast ocean.com on the surface but hiding currents below. Gravity was that current, steadily tugging matter into knots. As knots grew denser, they heated, preparing for a transformation that would change the cosmos forever. After roughly 200 million years, the first stars were born. These were not ordinary stars like our sun, but giant stars, or even hundreds of times more massive, called population 3 stars. They were pure hydrogen and helium, burning hotter and brighter than anything that followed. Their birth ended the cosmic dark ages. For the first time since the Big Bang, the universe glowed with starlight. The night was pierced by dazzling beacons, galaxies of newborn suns shining against the cosmic void. These stars lived fast and died young. Within only a few million years, their immense cores fused hydrogen into heavier elements, blazing with unmatched brilliance. Their light ionized the hydrogen around them, creating bubbles of transparency that spread across the cosmos. This era is known as cosmic reionization, when starlight stripped electrons from atoms transforming the universe from opaque fog into the transparent cosmos we know today. The heavens became clear, and light could travel freely across the expanding void. The first supernova erupted with unimaginable force, scattering heavy elements like carbon, oxygen, and iron into the surrounding gas. These explosions seeded the cosmos with the ingredients for planets, and eventually, life. From this stellar alchemy, the building blocks of chemistry emerged. Without these first stars and their fiery deaths, there would be no Earth, no oceans, no humans to gaze upward. In their sacrifice, the universe gained complexity. Meanwhile, gravity continued its relentless work. Clouds of enriched gas collapsed again, this time forming second-generation stars and the first galaxies. Small at first, these galaxies merged and grew, assembling into the grand spirals and clusters we see today. Imagine these galaxies as islands of light rising out of a cosmic ocean, each one containing billions of stars. Some grew into elegant spirals like the Milky Way, others into massive elliptical giants, and some remained small, dwarf galaxies that still drift today. With galaxies came structure on even larger scales. Under gravity's pull, galaxies clustered together, forming filaments and walls across vast distances. Between them stretched enormous voids, cosmic deserts almost entirely empty of matter. This grand zone, the cosmic web, is one of the most breathtaking structures in nature. From the tiniest quantum fluctuations in the Big Bang emerged a universe of astonishing beauty and order. Telescopes like the Hubble Space Telescope have peered deep into this past, capturing faint light from galaxies formed over 13 billion years ago. Each image is a time capsule, showing us the first sparks that illuminated the universe after its long darkness. The James Webb Space Telescope has gone even further, detecting some of the earliest galaxies, glowing red from the stretching of their ancient light. These discoveries confirm what theory predicted. The universe grew from simplicity into complexity, from darkness into light. Yet, mysteries remain. The first stars are too faint and too distant to observe directly, leaving scientists to piece together their story from clues in later generations of stars. But their fingerprints are everywhere in the elements around us, in the galaxies overhead, in the air we breathe. Philosophically, their story is profound. The first stars gave the universe its light, its structure, and its potential for life. They turned chaos into order, darkness into radiance. They remind us that creation often comes through fire and transformation. These stars also remind us of though they blazed with unmatched brilliance, their lives were brief, and their deaths violent. Yet in that destruction lay rebirth, the gift of heavier elements that would make new worlds possible. As galaxies multiplied, the universe became a vast city of light. Each cluster was like a neighborhood, each galaxy a home for billions of suns. The cosmos was no longer a dark void, but a glowing tapestry of creation. Gravity did not stop at galaxies. Over billions of years, galaxies merged into larger structures, clusters, and superclusters, bound together in webs, stretching hundreds of millions of light. These immense networks are the bones of the cosmos, holding everything in place. The Milky Way itself is part of such a structure, the Laniakea supercluster, a sprawling community of galaxies drawn together by gravity's invisible hand. Even our home is just a thread in this vast cosmic web. To visualize this is to see the universe not as random chaos, but as an unfolding design. From quantum ripples to galactic superclusters, the cosmos has woven itself into a structure both immense and intricate. It is humbling to realize that this grand structure began with the faintest ripples in the cosmic microwave background. From tiny imperfections in the fabric of space, the universe built its architecture of stars and galaxies. The first light of the cosmos did more than brighten the void. It marked the beginning of history as we know it. For without light, there can be no vision, no knowledge, no story to tell. The first stars opened the curtain on the cosmic stage. Today, astronomers continue to hunt for these ancient giants. By studying the chemistry of modern stars and the faint glow of distant galaxies, they reconstruct the story of those long-vanished suns. Though gone, their legacy endures in every element of our bodies. It is extraordinary to think that the iron in your blood, the calcium in your bones, the oxygen you breathe, were all forged in the hearts of those first stars and spread by their explosive deaths. You are, quite literally, made of stardust. From the silence of the dark ages to the roar of supernova, the universe's journey reflects our own. From darkness, we seek light. From chaos, we find order. From endings, we discover beginnings. The first stars lit more than the sky. They lit the path toward complexity, toward planets, toward life, and toward consciousness. They ignited a chain of events that would one day lead to beings capable of asking where it all began. Chapter 4 closes with this thought. When you look up at the stars, remember that the very first ones are gone, but their light lives on in you. Their fire is your fire. Their dust is your dust. The cosmos is not just out there, it burns within you. A legacy of the first stars that ended the universe's darkness. With the birth of the first stars and galaxies, the universe had emerged from its darkness. What began as a sea of hydrogen and helium was now a glowing network of starlight and structure. Yet this was only the beginning. From these early galaxies would come planets, solar systems, and eventually life itself. The galaxies grew by merging, colliding in slow-motion dances that took hundreds of millions of years. Every collision mixed gas, dust, and stars, triggering new waves of star formation. Chaos and violence became the architects of beauty, carving spirals and clusters out of raw cosmic matter. Gravity was the silent sculptor behind it all. In regions where gas clouds grew, especially dense, stars formed in great numbers. Their light illuminated the galaxies, while their explosions enriched them with heavier elements. Step by step, the simple chemistry of the early universe was transformed into complexity. Within a few billion years, galaxies like our own Milky Way began to take shape. From the outside, they resembled majestic spirals, arms unfurling gracefully across space. Inside, billions of stars glittered, each a potential cradle for planets yet to form. Our galaxy, the Milky Way, was born from countless mergers of smaller galaxies. It became a vast city of stars stretching 100,000 light-years across. Within its swirling arms lay clouds of gas and dust, nurseries for the next generation of suns and worlds. Stars continued their eternal cycle. They were born, they lived, they died, and in their death, they gave birth to new stars. This cycle gradually enriched the galaxy with the elements of life: carbon, nitrogen, oxygen, iron. Each generation added new ingredients to the cosmic recipe. Among the billions of stars forming, some systems began to produce planets. Gravity pulled dust and gas into swirling disks around young suns. Within these disks, particles collided, clumped together, and grew into rocks, worlds, and moons. In this way, the first planetary systems emerged. Some planets were gas giants, massive and volatile. Others were rocky, small, and dense, capable of holding atmospheres and oceans. For the first time, the conditions for habitability began to appear. Our own sun would not form until roughly 9 billion years after the Big Bang. Before it, countless stars had lived and died, seeding our corner of the Milky Way with the elements needed to create Earth. Our star was part of a second or third generation population, built on the ashes of giants. Around 4.6 billion years ago, the sun ignited within a dense cloud of gas and dust. As it blazed into life, a disk of leftover material swirled around it. From that disk, the planets of our solar system were born. The early solar system was a chaotic place. Countless asteroids and comets bombarded the newborn planets, shaping their surfaces and delivering water and organic molecules. Out of this chaos, the foundations of habitability began to form. Earth, the third planet from the sun, was one of the rocky worlds forged in this process. At first, it was a molten sphere, its surface a sea of magma. Over time, it cooled, forming a crust and releasing gases that created its first atmosphere. Water, delivered by icy comets and hydrated minerals, gathered into oceans. Lightning flashed over these primordial seas, and chemical reactions brewed complex molecules. In this cauldron, the spark of life may have first flickered. Meanwhile, other planets told different stories. Mars, smaller and colder, once held rivers and lakes but could not sustain them for long. Venus, closer to the sun, became a hell of heat and pressure. Only Earth remained in the delicate balance that allowed life to flourish. The link between stars and life is profound. Without the first stars enriching the cosmos with heavy elements, there could be no planets, no oceans, no living beings. Every breath you take, every cell in your body, carries the legacy of stars long gone. The universe had created more than structure. It had created possibility. Within the crucible of galaxies, the ingredients of life were assembled, awaiting the right conditions to awaken. Yet, the cosmos is not kind. Supernova, gamma-ray bursts, and black holes threatened fragile worlds. Entire planetary systems could be sterilized in an instant by cosmic violence. Life was never guaranteed. It was a miracle of chance and survival. Earth, however, found itself in a rare zone of safety. Our sun was stable, not too massive, not too dim. Our orbit was just the right distance for liquid water. Our planet was large enough to hold an atmosphere, but not so large as to crush itself under gravity. These just right conditions are sometimes called the Goldilocks factors. Earth was not too hot, not too cold, not too small, not too big. Against all odds, it was positioned perfectly for life to take hold. For billions of years, Earth has been sculpted by cosmic and planetary forces. Asteroid impacts reshaped its surface. Volcanoes remade its landscapes, and tectonic plates shifted continents. Through it all, life adapted, evolved, and thrived. The journey from galaxies to life is not a straight line, but a tapestry of connections. It begins with the Big Bang, flows through stars and supernova, gathers in galaxies, and culminates in the birth of planets and the spark of biology. Every living creature on Earth is a product of this chain of events. From bacteria to humans, we all carry the signature of cosmic evil. The iron in our blood, the calcium in our bones, the carbon in our DNA, all forged in stars. Inti Sensei life is not separate from the universe, but its expression. We are the cosmos made conscious, the universe reflecting on itself through human eyes. The formation of the solar system was a turning point in cosmic history. It was the moment when the grand story of galaxies intersected with the intimate story of life. From then on, the universe was not just matter and energy, it was alive. Scientists today continue to search the heavens for other worlds like Earth. The discovery of thousands of exoplanets shows that planetary systems are common, scattered across the galaxy. Some may even harbor oceans and skies like our own. This raises one of humanity's greatest questions. Are we alone? If the conditions for life arose here, could they not arise elsewhere? Perhaps somewhere, orbiting a distant star, life has also taken root, waiting to be discovered. Whether we are alone or not, Earth remains a rare jewel. Its blue oceans, green forests, and golden deserts stand as a testament to the delicate balance of cosmic chance. Nowhere else we know shines quite like home. The road from galaxies to worlds, from stars to life, is a journey of both chance and necessity. It required the precise unfolding of cosmic events, yet within that precision lay randomness, creating diversity and wonder. Chapter 5 reminds us that our story is inseparable from the story of the universe. To study the stars is to study ourselves. To trace the galaxies is to trace our origins. And so, the path continues. From galaxies and stars to planets and life, the universe has woven a narrative that leads directly to us. But this is not the climax, only the rising action. In the next chapter, we move closer to the ultimate questions, where this journey leads, and what destiny awaits the cosmos. The universe we inherit is a masterpiece of scale and subtlety. But even masterpieces have endings written into their fabric. From the smallest particle to the largest cluster, every component of reality is subject to change, decay, and transformation. The same physical laws that birthed stars and galaxies also forecast their eventual decline. Asking how it all ends is not morbid curiosity. It is the only honest way to understand the full shape of the story we inhabit. Observations over the last century have given us a startling revelation. The cosmos is not only expanding, it is accelerating. That acceleration is subtle on human timescales, but decisive on cosmic ones. A mysterious agent, given the name dark energy, appears to permeate space, exerting a repulsive influence that overwhelms gravity across the largest scales. Its existence reshapes the bookends of cosmology, turning the question of destiny into a problem of deep physics. If dark energy remains a gentle push, the universe drifts toward quiet loneliness. Galaxies speed away until they can no longer be seen. Cosmic light grows ever redder, and the night sky slowly dims. In such a future, known as heat death, or the Big Freeze, thermodynamic equilibrium wins. Motion, stars, and structure fade until only cold, low-energy photons and sparse remnants remain. It is an elegant but melancholic end. Order dissolves into uniformity. The alternative scenarios are as dramatic as they are speculative. If dark energy strengthens over time, it could tear apart galactic clusters, stellar systems, planets, and eventually atoms themselves, a catastrophic big rip. In that violent future, space would stretch so quickly that bound structures could not hold together, leaving a universe shredded into its most basic constituents. The scale and horror of such an ending are almost unimaginable. Yet physics allows it if the properties of dark energy demand it. Conversely, if the balance of cosmic forces tilts the other way, gravity might win. An ever-growing mass density could slow expansion, reverse it, and pull everything back into a final collapse. The Big Crunch. In that scenario, the cosmos would implode into a state resembling the one from which it began, compressing energy and matter into an ultimate singularity-like state. The Big Crunch raises age-old philosophical echoes. If there is a beginning, might there be a symmetrical end? There are also softer, cyclical ideas. The Big Bounce envisions a universe that collapses and re-expands, a cosmic heartbeat repeating over unimaginable epochs. Each cycle could reset conditions, perhaps with different laws or constants, meaning that our universe might be one chapter in an endless series. These models alter the conceptual stakes. Endings become transitions rather than terminations. Another radical possibility is that our cosmos is one pocket in a vast multiverse, where new universes bud off with varied physical laws. In that picture, endings are local. Universes are born, die, and spawn new ones in an eternal tree of realities. The multiverse idea reframes destiny. What happens to our pocket is small compared to the sprawling landscape of existence, yet it still matters deeply to the beings within it. Regardless of which of these futures is real, some trends are unavoidable. Stars will exhaust their nuclear fuel, galaxies will age, chemical complexity will decline. The universe's luminous youth is finite. The same fusion physics that powers suns will ultimately run down, leaving behind white dwarfs, neutron stars, and black holes, long-lived remnants that dominate a colder cosmos. Black holes are particularly intriguing in discussions of cosmic fate. They are repositories of mass and information, and they evolve by swallowing matter and merging with peers. Stephen Hawking taught us that black holes radiate very slowly through quantum effects at their horizons. Over stupendous timescales, even these titans will evaporate, returning their mass energy to the universe as weak radiation. The evaporation of black holes foretells epochs so long they boggle human imagination. Times when the last structures dissolve, and the universe is a dark, thin mist of particles. It is a realm beyond everyday intuition, where classical metaphors falter and entropy becomes the final arbiter. For some thinkers, this prospect is the most honest. Reality trends toward maximal entropy, inevitable equalization of everything. Yet the very mystery of dark matter and dark energy gives hope that current projections may be incomplete. These invisible players constitute most of the cosmos content, and their true natures might radically alter fate predictions. Uncovering what dark energy is could change everything. What now looks like an eternal drift might instead be a prelude to radical transformations unknown to present physics. Beyond physics, the prospect of cosmic endings carries a human weight. It presses philosophy and ethics into territory usually occupied by astrophysics. How shall we live if the cosmos is transient? If the long arc of time dilutes meaning? Some respond by embracing finitude. The fragile brevity of existence makes our brief moments luminous. Others find cosmic purposelessness liberating. With no ultimate teleology, Humans are free to craft their own meaning. The poet in us worries about loss. The slow extinguishing of the skies that taught our ancestors to dream. The scientist in us thrills at the vast processes playing out across eons. Both views are true. The cosmos is both mournful and marvelous, and a reader for wonder precisely because it changes and will in time. And there is also the practical question of survival. If intelligent life persists long enough, it might endeavor to influence its fate. Civilizations might migrate, cluster, or engineer their surroundings to survive longer. Technological species could, in principle, move between stars, harvest energy efficiently, and delay local declines. Whether any civilization could affect the universe's ultimate destiny, however, is deeply uncertain. Some speculative proposals suggest that sufficiently advanced intelligences could manipulate vacuum energy or engineer false vacua to create baby universes, a kind of cosmic reproduction. This raises profound ethical and metaphysical questions. Would creating a new universe be a moral act? Could it be an ultimate form of cosmic stewardship, ensuring that pockets of reality continue long after ours fades? The multiverse hypothesis also has implications for meaning. If countless universes exist, each with its own history, our cosmos is neither unique nor primary. Yet uniqueness is not the same as significance. Our local story still matters to us, and the relationships, discoveries, and lives contained here are no less real, because they are one among many. In modern cosmology, observation remains king. Telescopes from radio arrays to space observatories continue to refine our measurements of expansion, dark energy, and cosmic geometry. Each new data point chips away at uncertainty, narrowing the range of plausible futures. The better we observe, the more precisely we can sketch endings, and perhaps the more surprising the outcomes. Consider, for instance, the discovery that the universe is spatially flat to high precision. That fact is not merely aesthetic. It constrains models and informs fate scenarios. Flatness, combined with observed matter densities, suggests a cosmos where dark energy plays a central role. Still, subtleties remain. Small deviations or time-varying dark energy could change long-term predictions. Beyond measurements, theoretical advances may rewrite the cosmic script. A robust theory of quantum gravity, uniting general relativity and quantum mechanics, could illuminate what happens near singularities and in the universe's earliest instance. By symmetry, perhaps clarify its ultimate fate. The unknown physics of the Planck scale may be the key to endings. Even as the cosmos marches toward whatever destiny awaits, life in the universe counts as a radical anomaly, a local defiance of cosmic tedium. Life extracts order from disorder, builds complexity, and generates narratives. The emergence of consciousness means that the universe, briefly, can reflect on itself. That self-reflection is a rare jewel tucked into the fabric of time. From a human perspective, this is an ethical clarion call. If intelligent beings are indeed rare and precious, the responsibility to preserve and propagate life becomes urgent. Acting on such responsibility might mean conserving planetary biospheres, cultivating technologies to move among the stars, or seeding life elsewhere. Each choice alters the human story, even if it cannot change cosmological endings. The search for meaning then becomes an activity of creation, art, science, relationships, and institutions that outlive single lives are ways humans answer the silence of eventual endings. The cultural and scientific legacy we craft may be modest on cosmic scales, but immense for future minds that inherit our records. Memory, in this sense, is a bulwark against oblivion. The cosmologist's view does not diminish human significance. Itre frames Italiano. We are ephemeral but profound physical expressions of processes that span unfathomable durations. The narrative of the cosmos passing from hot tabletop of creation to cold expanse of entropy is wound through us, and our smallness does not negate our capacity for insight, love, or stewardship. Scientific humility also demands we hold multiple hypotheses about destiny gently. History shows that definitive verdicts often yield to new data and deeper theory. What once seemed certain is later revised. What now seems speculative might become orthodox. Thus, We live in a time of epistemic humility and grand curiosity simultaneously. Technological futures open further vistas. If humanity or its descendants survive and expand into the cosmos, they could reshape local environments to extend habitable eras, artificial structures, engineered ecosystems, and new modes of consciousness could make pockets of persistence possible well beyond natural planetary lifetimes. Such futures would be strange but beautiful emergent cultures that carry cosmic stories forward. Another intriguing idea is that information could be encoded in long-lived media. Artifacts stored in stable orbits, embedded in durable materials, or even inscribed at atomic scales. If civilizations anticipate cosmic silence, they could create messages intended to last until conditions change or new observers appear. These messages become acts of faith, a belief that the future might one day find them. The study of cosmic destiny also ripples back into how we approach science now. Priorities in physics, astronomy, and engineering are shaped by the questions we ask. What drives expansion? How to detect low-energy remnants? How to build sustainable futures? The practical and the philosophical co-evolve, tightening the weave between knowledge and action. When we contemplate ultimate endings, we are also compelled to cherish present marvels. The glow of the Milky Way, the cycles of seasons, the contingent brilliance of life all gain poignancy when seen against the backdrop of permanence's fragility. This poignancy can inspire reverence, stewardship, and an intensified commitment to understanding. So what should we take away as the curtain draws near? Neither despair nor hubris is the answer. Instead, a practiced wonder, an acceptance that our species arises in a cosmos of both grandeur and transience, offers a balanced way forward. We can pursue knowledge bravely, create responsibly, and love fiercely. In the end, the fate of the universe is a story still being written. Whether the cosmos fades into quiet, tears itself apart, bounces and renews, or spawns infinite siblings, our moment inside it remains incandescent. We are the universe's memory, its interpreter, and perhaps its most eloquent tribute. For a brief time, the cosmos lights a stage on which consciousness can flourish, and that, more than any forecast of ending, is a reason to wonder, to act, and to pass on the light.